Suppose there is a wall that is being hit repeatedly by some bullets. Let's say the bullets arrive one every 2 seconds. Each bullet is 3 grams and travels 400 meters per second, and the wall they hit is square with sides equal to 50 centimeters. What is the pressure on the wall due to the bullets? This is maybe a weird sounding question, but what it is meant to illustrate is one of the ideas that comes from the kinetic theory of gases is that the origin of pressure due to a gas is actually due to the collisions that the molecules make with the walls of whatever container they're in. But that can also include, say, objects in that container. So if there's people, say, in a room and we're experiencing air pressure, that would count, right? So it is kind of amazing, the idea that really comes from the kinetic theory of gases, that pressure really just amounts to some collisions. And so this, again, becomes sort of a model for that. But we've simplified things a little bit because in the conceptual picture we drew on the key concept slide, we said that molecules are moving around randomly with random speeds. In this case, we're looking at bullets that are arriving regularly, and they are all traveling with the same speed and in the same direction. And I'm doing that just to kind of simplify the picture into something that's a little bit easier to calculate, because when you say random, usually that means you need to do some kind of statistical analysis. And so I've taken that out to simplify the picture again a tiny bit. So the drawing I'm going to draw for this is, let's say this is that wall that is 50 centimeters to a side, and we have these bullets all coming in, and I'm going to imagine these are like really perfect rubber bullets that are coming in here. So what's going to happen is each bullet is going to hit the wall, but rather than embedding in it, is going to engage in a perfectly elastic collision. In other words, it's going to bounce off perfectly. So if each of these bullets is coming in with a velocity, let's say v, then when it hits the wall, it's going to bounce off with a velocity v going in the opposite direction. I'm just going to draw that below here because it's hard for me to draw that all kind of in one place. But here's like a bounced off bullet with a velocity v to the right instead of the left that it came in with. Now, I'm being asked for the pressure, and so the part of the goal here is to see how can this lead to a pressure. I mean, it might make sense that if these bullets are really tiny and if this is happening really fast, how this would just amount to some overall force being applied to this wall. And since it's distributed over an area, we could model that as a pressure, right? So since pressure is equal to force divided by area, that gives us maybe some clues as to what we need to do to actually calculate that for this situation. Now, the area part, I think, is relatively easy. That's just going to be 50 centimeters squared, since each side of the wall we're looking at has a side of or a length equal to 50 centimeters. So just square that, right? But how do you do the force? Well, there's maybe a couple ways of thinking about this. One statement that maybe is the easiest way, I can think kind of two ways of looking at it, but one that's kind of easy is to say, well, what if we look at impulse? Impulse is equal to force times time, but the impulse momentum theorem says that that is equal to the change in momentum. Now, I said there's kind of two ways to look at this, because the other starting point would have been like, well, force is also equal to change in momentum of a system. In other words, F is equal to delta P over delta T, but that's really just algebraically the same thing, just multiplied by delta T on both sides, right? So whether you think about it as impulse is equal to change in momentum or force is equal to the time rate of change in momentum, they lead to the same place. What I'd like to do, though, is calculate. So like if I look at the solution for force here, and I say, okay, that's equal to delta P over delta T, and then what I'm going to do is actually calculate, based on the numbers that are given to me here, what I think this delta P over delta T should be. So each bullet has a mass of 3 grams. So remembering that momentum is mass times speed, or mass times velocity, I'm going to say 0.003. I'm going to convert to standard base units, kilograms for that mass, multiplied by 400 meters per second. That's clearly a momentum. However, because in the picture the bullets are bouncing off elastically, this would be the amount of momentum lost if a bullet just came and like hit the wall and then dropped down or something like that. But we didn't even say there was gravity, though, so maybe it would just sit there, right? But we're saying it bounces off, so that really means the total change in momentum should be 2 times what we're calculating here. So let me make sure to remember a multiplication by 2. And then since these bullets are kind of coming in at this regular rate of 1 every 2 seconds, I'm just going to assign the 2 seconds to the delta t. In other words, every 2 seconds, this is happening. And so that is going to be the force that I think those bullets exert onto this wall. So if I calculate what that is and then divide that by area, I should have a pressure, right? So pressure in that sense should be equal to 2 times 0.003 kilograms. I didn't even bother to calculate what this is. If you want to, you could, but it's not really a final result. And since I didn't do it, I'm just going to take this and then divide the whole thing. So I'm in a quandary. How do I want to write this? Just make a big line here. Divide by, since I'm doing everything in base units, I said, and I'm doing that just because I want to get a result in maybe newtons per meter squared. And I think if I don't convert to base units, that's going to be hard to get to. But I'm going to take 0.5 meters and then square that here. So this is the thing I would like to calculate. And I believe if you put that in the calculator, you wind up getting 4.8. And let's look at the units there. I'm expecting newtons per meter squared, and I think it's there because this is kilogram meters per second, so that's a newton. And then it's per meter squared, so this should be in newtons per meter squared. If I wanted to, I could state that as a Pascal unit, although newtons per meter squared is cool as well, I think. Let's see how that lines up with the answer. It looks like in the answer, they've actually done some of the calculations that I skipped over. Calculating that momentum to be equal to 1.2 kilogram meter per second, and then recognizing that's the momentum of one bullet coming in, so you have to double that because of the elastic collision, meaning the change of momentum that's kind of being imparted to this wall is double the amount of momentum a single bullet has, so that gives you the 2.4 kilogram meter per second. And then it looks like it's saying here, I think it's saying force is equal to impulse over time, which is equal to change in momentum. So I did slightly different notation in the slide. But since that's going to be 2.4 divided by 2 seconds, that's where I think I got the 1.2 newtons from there. And then I said, okay, pressure, force divided by area is 1.2 divided by 0.5 squared, yielded 4.8 newtons per meter squared, which aligns with what we got.